Hello, Professor. This is Janatul Mawa presenting a review paper on an optimization-based feasibility analysis of a zero-emission energy system for a remote coastal community in Canada. Firstly, I would like to emphasize the importance of this topic. I used some keywords like cost-effective power supply, zero-emission, renewable energy, clean power generation, and sustainable power supply to select my topic. After selecting the subject, I chose 23 papers based on the abstract, which actually matches with my interest. This topic is important as we need a more sustainable and cost-effective power supply to fulfill the needs of our citizens. And moreover, the necessity of clean power generation is a demand nowadays because of the huge climate change. Additionally, reusable natural resources and lack of fossil fuel are a constant area in this paper. Moreover, one of the most important parts is the recent price hike issue, which is discussed here. Canada is a well-developed country with various kinds of natural resources. The energy demand is increasing daily because of technological advantages, improved living standards, and population and economic growth, which might create an imbalance between the need for energy and the supply. In Canada, electricity is generated from different kinds of resources. In 2018, the energy mix included 7% of coal, 7% renewable, and 11% natural gas, 15% of nuclear, and 60% of hydro. Though Canada is the world's third largest producer of hydroelectricity, around 2 lakh of people are disconnected from the natural gas and national grid distribution line. In some isolated coastal regions, grid extensions are not feasible because of the economic, geographical, technical, and climate limitations. The Canadian government is very much concerned about the climate change diminution. The government emphasizes more on clear power generation and has already prepared a policy framework to tackle the climate change. To have a clear energy system, the program focuses on the alternative use of the diesel-based system to reduce the emission of greenhouse gas. The province of Newfoundland and Labrador generates 80% of its electricity from renewables such as solar, hydroelectricity, and wind. Energy from renewable sources is the most efficient and clean alternative to fossil fuels to supply energy to disconnected communities. The paper summarizes the significance of analyzing the proposed topic to satisfy the remote area electricity supply, to make a framework to comfort climate change and emphasize more on clean power generation and the optimal component sizing of hybrid systems for a cost-effective and sustainable solution to supply stable power in the off-grid area. The paper mainly investigates the contribution of a zero-emission system for PV, wind, hydro, PHS hybrid system to supply reliable power to a remote coastal community in NL. To achieve the desired goal in this proposed paper, I went through around 23 papers that describe the condition of the energy sector globally to study the emission rate and cost effectiveness. Many studies have reported optimal sizing and performance analysis of standalone hybrid energy system with hydro options, integrated as standalone hybrid photovoltaic battery option to electrify a coastal community. In another study, it was reported a feasibility study of a hydrokinetic PHS and hydrokinetic battery system in South Africa and found that the PHS based hydrokinetic option offers lower electricity costs and is more environmentally friendly than the battery based option. Optimized a standalone PV hydro diesel battery system for rural electrification in Iraq. The results of their analysis showed that the optimized hybrid system has a cost of energy of $0.054 per kilowatt hour and net present cost of $1,13,201. The system is environmentally friendly with renewable penetration of 91.3% and generates only 16,968 kg of carbon dioxide annually. Recently, a PV, wind, hydro, PHS-based hybrid option was optimized using multi-objective particle swarm optimization (MPSO) for the standalone application in China and proposed a PV hydro PHS battery system for powering a single house unit. In their study, both the hydropower and PHS were operated from directly rainfall and the rooftop was considered as upper reservoir. The present study for the proposed hybrid options considers four aspects. Firstly, the cost-effective and reliable PV, wind, hydro hybrid system with PHS based on the minimum COE and NPC. An economic and environmental analysis of PHS with the battery system. The third one is the comprehensive sensitivity analysis to examine the effects associated with the uncertainty of meteorological resource data, load data, and pipe loss on optimal sizing. And lastly, the cost effectiveness and environmental benefits of the optimized system. I reviewed three methodology. Firstly, I will be describing the community load assessment. The electrical load assessment is the primary input while designing any hybrid system. The load demands mainly depend on weather condition, living standards, personal income, and geographic location. Canadians usually enjoy a high living standard due to their strong economy. Initially, the load profile is assessed from a grid-connected single household utility meter, and then the daily load demand is calculated as shown in this table. The community load is then estimated by multiplying the daily load by 50 to get the community load. Based on the load profile, the peak load is 577.84 kilowatt. To make the standalone RE-based studies more accurate, a range of 20% randomness in load demand is applied. A 5% randomness is used daily to make the load profile more realistic. The hourly load demand distribution for the summer and winter seasons for the entire community will be illustrated in the next figure. The load profile clearly shows the load variance throughout 24 hours of a day, the peak load requirement in the evening, and the minimum midnight for the residential community. The maximum peak occurs between 8 to 10 and the minimum between 3 to 6 hours for both seasons. The consumption is higher in colder months than in the summer. In addition, electricity consumption is a maximum in February and a minimum in August. Recently, the tariff for island consumers has increased the compensate for rising fuel prices. An island consumer has to pay 12.2 per kilowatt hour, while the energy rate is $3.15 per kilowatt hour for grid-connected consumers. Secondly, the system components. The hybrid system entails a PV module, wind turbine, hydro, PHS battery, and converter. The study considers a monocrystalline E-series solar module of rated capacity of 327 watt with 20.4% panel efficiency. The rated voltage and current of the panel are 54.7 volt and 5.98 ampere respectively. The PV module needs a capital cost of $1,300 per kilowatt and an operating cost of $20 per year. The lifetime of a PV module is 25 years, and the project lifetime is also considered the same based on the PV. Wind turbine. A 20 kilowatt rated wind turbine is selected for this study. The rated cut-in and cut-out wind speeds are considered as 8.5 meter per second, 2.75 meter per second, and 20 meter per second respectively. The replacement cost is considered as 1750 kilowatt, 70% of the capital cost, and the O&M cost is $50 per year, which is 2% of the capital cost. For the hydro, in this study, a small hydrokinetic turbine is considered. The system runs by a continuous flow of water, thus require no dams for reservoir. A 100 kilowatt water turbine is used in this study depending on the available head and discharge rate in the selected location. The capital replacement and O&M cost of the turbine are $700 per kilowatt, $500 per kilowatt, and $51 per kilowatt year respectively. The zero-emission hybrid option is compared with the diesel-only system in terms of cost and environmental perspective. In this regard, a diesel generator-based option is considered in this study. A diesel generator with 25% minimum starting threshold is designed for its longer operating lifetime. The cost associated with capital replacement and O&M are 370 kilowatt, 296 kilowatt, and $0.05 per hour respectively. And thirdly, the economic analysis. The economic analysis always plays a vital role since the hybrid energy system should be economically feasible commercially to attract the government and investors for successful implementation. Although the initial investment is very high for a hybrid system, it would be very beneficial over a long operating period. Moreover, the cost is comparable to the investment of the government and the different NGOs' climate change mitigation policies. The economic performance among various systems is mainly based on the cost of energy and net present cost. The cost of energy, COE, is determined using the equation 1 here, which is COE is equals to CA divided by ES. CA is the total annualized cost and the total annualized cost is the summation of annualized capital, replacement, and operation and maintenance cost. The net present cost (NPC) is calculated using the equation number 2, where CRF is the capital recovery factor obtained and the actual discount rate is calculated. The entire project lifetime is 25 years in the present study, while an annual inflation rate and nominal discount rate are considered 2% and 8% respectively. The International Energy Agency, IEA, proposed a diagram for the PV wind hydro PHS and PV wind hydro battery hybrid system. I got the results from 3 configurations from this review paper. The first configuration is A1, which includes PV, wind, hydro and PHS. Second configuration includes the wind, hydro and PHS. The third configuration includes the PV, wind and PHS. From the first one, the configuration 1, it is evident from table 2 that the optimized system, the A1, consists of 15.2 kilowatt PV, 100 kilowatt wind turbine, 98.1 kilowatt hydro, 326 kilowatt inverter, and 4,575 kilowatt hour PHS capacity. Hydro and wind contribute more than 98% of total energy generation, while PV generates only 18,762 kilowatt hour per year due to low PV capacity. The excess energy is 4,74,992 kilowatt hour per year, which is relatively high, and the unmet load demand is negligible. The cost components are described in the figure. The capital cost of the system is 9,33,584. The PHS is the dominating cost component, which consumes 42.4% of total capital cost, and followed by wind is 26.78%, hydro 18.2%, and converter 10.47%. However, PV needs only 2.1% of capital investment. The second configuration, the wind, hydro and PHS option, the cost summary of the second configuration is illustrated in the figure. The configuration consists of 100 kilowatt wind turbine, 98.1 kilowatt hydro, 354 point inverter, and 4,829 kilowatt hour PHS. The cost of energy for the configuration 2 is $0.139 per kilowatt hour and is very competitive with the best configuration 1. The capital cost is the significant expense of the total cost, which comprises the initial investment cost of wind and hydro, operating and replacement cost. PHS is the principal cost component in both capital and operating costs, closely followed by wind turbines. The system offers outstanding environmental benefits, and the NPC, the net present cost, is $16,27,062. The third configuration, A3, with a PV wind PHS option. Among these 3 configurations, A3 is the worst option. It eliminates the hydro turbine and has a comparatively higher cost of energy of $0.194 per kilowatt hour and NPC of 22,66,739 due to the large PV module and wind turbine. This configuration includes 77.7 kilowatt PV, 400 kilowatt wind turbine, 425 kilowatt inverter, and 5083 kilowatt hour PHS, which are comparatively larger than the configuration A1 and A2. The wind turbine supports 17,25,385 kilowatt hour per year, while PV generates 95,859 kilowatt hour per year to meet the load demand. The configuration produces maximum excess energy of 8,57,261 kilowatt hour per year, which is almost 44.6% and 46.9% higher than the configuration 1 and configuration 2 respectively. In the configuration 3, the larger capacity of PV module wind turbine and the PHAs are required to satisfy the load demand. The summary of the cost flow is shown in the next figure. The wind turbine is the dominating cost component in the capital, which is 7,50,000 and replacement cost, but PHS has a higher operating cost compared to the wind. In this review paper, the main objective was to find a feasible solution for optimizing a zero-emission energy system. In this prospect, I selected these papers from different categories and also considered some papers which are not feasible because they had some attractive features. In this paper, I tried to analyze the economic possibility of the projects of the research paper I chose. There is an important part that most of the papers did not cover, that is the consideration of an efficient energy storage system for emergency cases. The most cases, generators are used as a backup power sources, which is becoming expensive daily because of increased fuel cost. This is the reason for researching efficient energy storage system as a replacement for fossil fuel generators. In the analysis part for different projects, I tried to show the technical and economical analysis part of different projects and showed economic analysis. The analysis shows proper documentation and future prediction for a small-scale power generation plant. That is all from my presentation. Thanks for being with me.